Hello and welcome to the SageMath lecture series. In today's lecture, we are going to introduce certain number theoretic functions available in SageMath. These functions are the Gcd function, the LCM function, and the Bezos identity coefficient function. We will also see how to compute the Euclidean Gcd using division algorithm in SageMath. Also, we will see how to express the Gcd of two integers as a linear combination of the two integers. To start our computation in SageMath and in number theory, we are going to create a new SageMath notebook. Note that I am already in the SageMath Jupyter interface using my Firefox browser. I am creating new SageMath for notebook. So the SageMath notebook is open. I am going to give some name for that. 003 SageMath number theory. I am giving that name. Now, the very first operator that probably one learning number theory requires is the remainder operator. So, remainder operator is the percentage operator. So, remainder of 15 divided by 4. Pressing shift enter gives equal to 3. Remainder of minus 15, 4, that I get as 1. Now, to compute these two things in the same line, we may use the print function available in Sage, and we can include both these lines in a comma separated. Both these computations on the same line, they get remainders to be equal to 3 and 1. Now, once we find the remainder in the division theorem, we know that given b and a, we need to write b to be equal to a star q plus r, where r is the remainder. So suppose that we are choosing b equal to 1076 and a equal to 272, some randomly chosen integers. Now how will you, we already know that how to find this r is nothing but b percentage a. Now how to find q? So q is nothing but q is equal to b minus r by a. So q is equal to b minus a divided by b minus r divided by a. Let's see what the output is. Print q r. We are going to print both, and we will get equal to 3 and 260. Now the division theorem statement also we can print exactly in the same way. So for printing the division theorem statement, we are going to do something extra. So b we need to print as a value. After that, we need to print the equal to symbol, that is enclosed in quotes. We need to print the value of a. We need to print a star symbol corresponding to function. After that, we need to print the value of q. Now we need an equal to aq plus r. Now we need a plus symbol. Now we need the value of r and everything included here. So if I press enter, I will get 107 272 into 3, 260. This is what the division theorem statement is. Now we are going to see how to compute the Gcd of two given integers. Okay, we will choose b and a to be exactly the same numbers. Recall that Gcd, by the definition, it is the largest element in the set of all common divisors of a and b. So we need to find divisors of a first, set of all divisors of a, set of all divisors of b, and then we need to take the intersection of these. We are going to take the set of all divisors of a, and let us call the set of all divisors of a equal to div a, and we are forming that set. Set divisors. Divisors is a special function. Set is another function. Set of all divisors of a we found. So let us print and see how does it look. Divisors of a, here it is 1, 2, 4, etc. Okay, now we are going to find the set of all divisors of b also here. So just change, instead of a, just write it to be b. Set of all divisors of b, and print the set of all divisors of b, and the result is. Now we find the intersection of these two sets. How do we find intersection? In Sage, to find the intersection, we need to use the dot intersection, div A dot intersection div B, and otherwise we can use div B intersection div A. These two statements will give the same output. Now let us print set of all common divisors, and the output is 1, 2, 4. Now the GCD is the maximum of these, so print GCD. What are the two numbers we have? A, B, and E is enclosed in quotes. Is, what is it? Maximum elements in CD. Let us print even that. Output is GCD of 272.1076 is 4. See, how did we use the print statement? So here GCD of, we wanted to appear exactly like that, therefore we enclosed it in quotes. A and B, we wanted the value of A and B to appear, there is no quotes. Is, we wanted to appear exactly like that, there is no quotes. And max of CD, max is another command in Sage. Of course, you can guess that there is a min command also. Fine. Now the GCD is found. Now after finding GCD in this way, the Euclidean algorithm is another way to find GCD. So we are going to see how to use Euclidean algorithm to find GCD. So to find Euclidean algorithm, to use Euclidean algorithm for finding the GCD, we need to execute the division theorem in several steps. We need to perform division in several steps. Let's take the same A and B taken. Now we need to write the division theorem. We need to find R, we need to find Q, and we need to write the division theorem statement. Okay, let us copy this. We are going to repeatedly perform division here. So repeat division here. So R is equal to B percentage A. Q is nothing but it's equal to this. And I tell that we can, instead of Q, one can, using this Q is equal to B minus R by A. There is another function available in Sage for finding the quotient. Insert a new cell. Know this. That function is nothing but floor. Floor function. In mathematics we call that as the greatest digit not exceeding. The floor of, what are the numbers? 1076 by 22. That will give you the quotient exact. What is the output? Output is just 3. See that here also it's 3. So floor function also computing the quotient. So we are going to use floor function here. Floor of B by A. So print Q and R. This is not necessary. Okay, we will see the output. What is the output? We get 1076 is equal to 272 into 3 plus 260. The next step, we want to write 272 is equal to something into 260 plus the remainder. So exactly the same steps, but the only difference is that the value of B not be the same. The value of B should be equal to 272, which is A. Value of B should be A, the value of A, and value of A should be nothing but it's the remainder. But we should not write like this, but instead value of B and A becomes A and R. This is what we are going to do, and we are going to repeat the computation using the new B and new A. Let's see what happens now. So 272 equal to 260 into 1 plus 12, exactly the same thing. Now we want to repeat this. Again, we want to change the value of B now. Now B should become equal to 260, A should become equal to 12. So B should be equal to the value of A should become the remainder 12. Let's see the output. It's now 260 equal to 12 into 21 plus 8. Now exactly the same procedure we are going to repeat, but with different values for A and B, and we get the output 12 equal to 8 plus 4. Maybe we can the remainder, we are not getting the remainder to be 0, reading it. Okay, finally we got the remainder to be 0. Therefore the GCD is going to be equal to the last non-zero remainder, which is 4. So we found the GCD. But one important thing here is, here we are copying and pasting the same command in each and every step. Same command here, etc. So instead of copying and pasting the same command several times, we actually use something known as a while loop in SageMath. So how do the while loop work? We'll see now. So for the while loop to work, let us take the values of a and b like this. Now we are going to, how many times we have to perform this division theorem? We don't know. So we are assuming that we may have to perform infinitely many times, but don't worry about that. We know that when the remainder becomes 0, we have to stop. So we will put a condition inside. So see that I am going to type after some space left from the margin. So the statements are exactly the same. Is equal to a, r is equal to b percentage a, etc. So b and a already given. So r is equal to b percentage a, b is equal to this. Now we are finding this. R equal to 0, we will not proceed. If r equal to 0, if r equal to 0, we want to stop this procedure. We want to stop the execution of computing remainder again and again, computing the by division theorem again and again. So if r is equal to 0, we will stop this loop or break this loop. But remember that we need only non-zero remainder. Therefore, instead of checking this r, we will check if b percentage a is, that is, the remainder is 0 or not. If b percentage is non-zero, then only we will mark that b percentage a as the remainder, r equal to b percentage a. So if we continue this, let us see what happens after that. Just execute this. So, infinite loop is coming up. See, this is the problem when we are having this what you call infinite loop. See, here we have not changed the value of b and a. That is the mistake that we did. Here we have to change the value of b and a in every step. So we need to put an extra condition. I am stopping the execution here. Interrupt the kernel. Stop. Now I am going to see here that b percentage it is changed. Therefore, I need to, why should I do that? After printing the statement, I need to interchange the value of b and a. So let us see what happens now. Okay, so we are getting 107672 into 3 plus 260. 272 is equal to 260 plus 1 into 12, etc. 12 equal to 8 into 1 plus 4. After that, the remainder became 0. So what is the last remainder? So r is the last remainder, because if b percentage a becomes 0, we have not put the value of b percentage a into r. Therefore, r is now having the least value inside that. So the GCD is nothing but it's equal to, say, the GCD is nothing but that is equal to r. GCD is 4. So this is how we compute GCD using division algorithm and Euclidean algorithm and while loop. But the interesting thing is that, not very surprising, you can easily find the GCD using a direct command available in SageMath, which is print GCD of 10, what were the numbers that we have taken? 1076, 272, 76, 72, and the output is 4. So we have a quicker way of finding GCD. There is no need to perform computations using Euclidean algorithm. Already the GCD is there. Now you can immediately say that what is the command that we have to use for finding LCM. So it is just LCM. That is 73168. It's a big number. Now to find the GCD of 3 numbers, what do you do? 6, 3, 10, 12. GCD of 3 numbers, if you try to find, now this is creating an error because this is not allowed. So to find the GCD of more than 2 integers, we need to enclose the numbers in square brackets. Square bracket enclosed numbers is known as a list of numbers. Equal to 2. GCD is 6, 10, 12. GCD is 2. Now we can verify one known result in our theory, which says that LCM of two numbers into their GCD is equal to the product of two numbers. Okay, let us see if it's correct or not. What is our A? What is our B? A is chosen to be this. A is chosen to be this. B is this. Let us see LCM of A, B, star GCD of A, B. Is it equal to A star B? That's the question. SageMath says that it's true. So SageMath has verified that LCM into GCD is going to be equal to the product of numbers, at least in this. Now we are going to express the GCD of two numbers as a linear combination of the two numbers, which is that identity is as Bezos identity. Bezos identity is nothing but D equal to AX plus Y, where D is the GCD of A and B. So we need to find X and Y satisfying D equal to AX plus. Okay, we are going to take the same example here, B equal to this and A equal to this. So to compute this, there is actually an interesting technique which states that we can write, okay, I will show that in writing, I think that's better. So I'm going to use my green board. My green board is here. The numbers we had is 172 and 276. Just remember that. So 172, B is equal to A is like that. But I have to express the GCD. I have to be computed equal to GCD by whatever it is. So GCD is nothing the last non-zero remainder. So if I am able to express each and every remainder while performing the division theorem, the division, then I can definitely express GCD also combination. So technique is this is equal to 1 in 4 in similarly 2 1 0 1 into. So what we are going to subtract from 1072 as many number of times 76 we can subtract. That means 72 the floor of that, if you take that is the quotient, and suppose that the quotient is that once we'll subtract 1072 this many times this. So what we are going to do is we are going to subtract 1072 107 plus 0 in root 76 minus, so how many times? 2 times. 2 into 276 is equal to q into 1 to is what we remainder that we are getting for the first, call it R1. Now this is 1072, 1072 is common, therefore it's going to be 1 minus q. So only on the coefficient of 102 here we are performing computation. 72 0 minus 0 26. Next step is from this expression 276 equal to 0 into 1072 plus 1 into 276, we will subtract as many times as we can subtract this remainder. So we keep on subtracting like that. So then we will get this is the first remainder, then we will get the second remainder. then we get the third remainder. The last non-zero remainder, see here that remainder 1 is expressed as the linear combination of 1072 and 276. In the next step, we will subtract from 276 equal to 0 into 1072 plus 1. Subtract as many times R1 possible. But remember that subtraction is taking place only on the coefficients. Therefore, we are going to focus only on coefficients in the following way. So this computation we can probably write as 10710. This is 1 into 107, 0 into 266 to 0, 1. So for perform multiplication, multiply this with q, then we get a result. Q 0, 1. The remainder we getting here q2 1, because the next remainder are the linear combination of this 1072 and 276, and we keep on doing like that until we get the remainder to be equal to 0. This is the procedure that we want to follow. Okay, now we are going to perform these computations in SageMath. So to perform this computation in SageMath, remember that we wrote 102 and after that 1, after that 0. That is a kind of a row vector. So we are going to define a row vector by the name v1. 1 equal to vector consisting of 1072. After that, it is equal to 0 into 1. So to 1, because we use the fact that 1072 is nothing or 1 plus what is the number 272 or 0. Okay, this comments I am enclosing, I'm proceeding with a hash symbol. Now after that 272 to 0 plus 172. Okay, this is 1072 272 into 0. So therefore 1010 1 0 and vector is closed. So this is a vector. Print v1, you can see we did 1072 1 0. Similarly, we are defining is the row corresponding to, it's a vector corresponding to 270. Now v2 is equal to 2 0 1, and now we are going to make some subtraction. What is the subtraction? We need to subtract q times. We need to find q is nothing but it's a floor of the this b and a are now here as v1 0. V is nothing v1 0. A is nothing but v2 0, because the elements here are, this is the 0th element, this is the 1th element, this is the 2th element. Floor of v1. So see that I am enclosing the 0 in a square bracket divided by v2 at q. Let us see what this q is 3. See that in the previous step we had this q is equal to 3. So this is here. Now we want to subtract. See, from v1 we want to subtract q v2. Print v1 or 2, and what is the result? Minus v1 minus, the result is 256 1 minus 3. See that 256 07 76 270. 260 is the remainder. Here there is a small mistake. Here we have taken p equal to 107 and here it is 1072. So 76. So we get 260 equal to 1 minus 3. Now we are going to change the roles of v1 and v2. v1 will become now equal to, because we want to now from this 272 row we want to subtract whatever new thing we got. So 272 row we will convert that as straight there as v1. New v1 minus q v2 we will take it as v2. So v1 v2 equal to v2 q v2 q. So okay, we are going to disable this print command. Also see what is the result. v1 v2, let us see if it changed or not. So we are getting 72. 272 is this row. 260 is the next row. We are going to continue this with. We are going to again take the floor. So we get the new vector as 12 minus 1 4. See, finally as 12 minus 1 4, that means 12 equal to minus 1. Okay, we didn't get the remainder. Okay, continue this for another step. Next step, 12 minus 4 8. And that once again exactly the same. So we get 4 equal to minus 23 into 1076 plus 91 into 260. Okay, let us see, was 4 the GCD? Yes, the GCD was 4. Therefore, we finally get that this is the resource identity coefficient. 4 equal to minus 3 into, okay, let us verify that. 4 minus 23 into 107 21 272. We get us. So the resource identity coefficients are minus 23 and 91. So we computed resource identity coefficient directly. But of course, in SageMath there is an easy way to do even this thing. So we need to just find the Gcd of 076. That turns out to be equal to Gcd turns out to be equal to 16 . So this is 6. 4 equal to minus 20 into 172. This is what the resource identity coefficients are. We can directly also find the coefficient. Next, we are going to solve a linear definite equation in two variables using the resource identity coefficients. To see how we are going to do that, I'm going to show my code and going to perform some computations here, some quick computations. So basically what we are going to do is to solve AX to the linear definite equation. Suppose that we have the linear definite equation AX plus by c is solvable. We know that this is possible, and only the GCD d equal to divide c, where d is of a and is not to us. Now if d divides c, then we know that c is equal to into d4, and in that case, suppose that if x naught y naught is a solution, not y naught solution for that, we call this as 1, then by multiplying m on both sides, that here e is equal to that, therefore by naught equal to b. If you multiply with b, we get a. Multiply with m, b equal to md, which is equal to c. So we have to find a solution for once we find basis identity coefficients x naught and y naught, we need to just multiply that x naught and y naught with m, and then we get a solution for ax plus equal to c. So this is the technique that we are going to employ for the GCD of finding a solution for the linear Diophantine equation. Now we are going to solve a linear Diophantine equation. Coming back to Sage, suppose consider our equation is something like, suppose the linear Diophantine equation we are going to solve is the LDE 1076 x plus 272 equal to 24. So the first step is to make sure that first step is, of course, we have to define A and B. So A is 1076, B is 272, and is 24. The first thing we have to verify is if the GCD divides C or not. If GCD of A, B, we cannot write like that. If C percentage of D equal to G B, if C percentage D, the remainder, if percentage D equal to 0, say that D is solvable. Now, how will you solve them? You need to find the identity coefficients. So if C percentage D is equal to 0, we are going to find the Bezos identity coefficients. Suppose we call the Bezos identity coefficients as BIC. BIC is GCD A and B, and let us print that. Print BIC. Print BIC, we get a 4 is solvable and minus 23, 91. So, but the problem is we need this minus 23 as x naught. We need to take this minus 23, 91 as y naught. So solution is going to be, you know, that x naught is equal to the second number in the pick 1, because numbering is like 0, 1, 2, etc. Y naught, the solution for x naught 1076 equal to the GCD, which is 4, not equal to pick of 1. So the solution is given LD is LDE, we need to multiply x naught with C by D, because D divides C. Otherwise, we will just write M equal to D by D. Solution is x naught star y naught star. Solution for the given LD is minus 1, minus 1. Let us see if it's correct or not. Print minus 138. We need 170. Oh, there is a mistake. Once y naught is also taken as pick. So the solution is minus 138, 546. But now, if the GCD is not dividing C, then we need to print else that the LD is solvable. So for example, suppose that we are considering here, in this case it is solvable. Now suppose that otherwise we are considering a non-multiple of 4 in this. Suppose that we put it as 21. Solution for not here. The LDE is not solvable. So the LDE is solvable if and only the GCD divide C. So we have completely found how to find the business identity coefficients and how to solve two variable linear equations using resource identity and SageMath. Now, how do we find the general solution for this? Let us solution x. General solution. Find the general solution. So we know that the general solution x minus x plus b by d into t and y minus a by d into t, where x naught minus a by d into t and y naught plus b by x naught plus b by d into t and y naught minus a by d into t is the general solution. That we require the variable t is necessary. We are going to define here. So this is therefore something known as a particular, not the general solution. For finding the general solution, by the following, we are going to define symbol or a variable, and now in the general solution, but solution one solution plus what do we need? D to t star t here m minus a by star. Let's see the output. Okay, we need a comma and so general solution given LDE is minus 38 or otherwise minus 38 plus 60 and 546 plus 269t. So SageMath can give the general solution also using the Pearson's coefficient Pearson's identity technique. So with this we are stopping today's lecture session on SageMath, and the topic we discussed was elementary number theory, and in that topic we discussed GCD, LCM, solving two variable linear Diophantine, etc. We will continue with more topics in number theory in the next session. Thank you very much.